All right, guys, welcome back. Hope you guys had a nice, nice Monday off. So let me just go over our calendar real quick. Unit 3, there's not a whole lot to Unit 3. It was mainly chain rule and implicit. And then we did derivative inverse function Friday before we left, where we had to just understand the relationship between a function and its inverse. Order pairs are flip-flop, but the slopes are going to be reciprocals of each other. And so the rest of this unit is just, let me see, 3.4. It's just more derivative rules for us to, apply. And there's a little bit of, log differentiation. That's not too bad. So we have 2 more days of content, and then we'll start putting it all together Thursday, Friday for our test. So our test is typically units 2 and 3 are kind of 1 unit, but I split it up into 2. So unit 3 test will cover unit 2 as well. So it'll have power rule, product rule, quotient rule. I've pretty much finished grading your quizzes, so I should get that back to you by Thursday. So I'll have it back to you by Thursday. So and then on Monday we're going to start unit 4, but they'll give you an extra day to review, and then a test will be next Tuesday. I'm probably going to start having help sessions probably Monday and Tuesday morning. So once I have that figured out, I'll send that out and I'll post it as well. All right, so page 20. So we have a couple of notations for inverse functions. Sometimes you may see inverse sine of x with that -1 notation exponent, or you may see arc sine of x. So these are kind of interchangeable. So I'm going to use arc sine, but inverse sine, they mean the same thing. We're going to go back and revisit all of our derivative rules with chain rule built into it. But since we just learned chain rule, I'm going to have them all built into the derivative rules. The reason why I like having a chain rule built into all of our derivative rules is so that we can always look for it. We always assume that there's chain rule, and if there isn't, then it'll just be ×1. So it's not a big deal if there isn't a chain rule within an easier derivative problem. But I think if we always have it built into the rule, then we're always forced to look for it. So arc sine of u's derivative is u prime over the square root of 1 minus u squared. So whatever is inside the arc sine function is your u value. So that u value can just be an x, or it could be like 3x squared, or it could be 5x plus 1. But whatever is inside that location is your u value, and you're always going to take the derivative of that term. Again, if it's x, then u prime would just be 1. If it's 2x, then u prime will just be 2. All over the square root of 1 minus u squared. And u is going to be, again, whatever is inside that arc sine. Right. Arctangent, the derivative is u prime over 1 plus u squared. And then arcsecant derivative is u prime over the absolute value of u square root of u squared minus 1. The nice thing again about I like labeling it in this format because again I have all this the C trig derivatives all lined up, and they're all going to produce negative derivatives, just like how we did with the original sig trig functions. But in this case, this is even easier because all we need to really know are these three, because the three that are across from arcsine, arctangent, arcsecant are basically the exact same rule, just with the negative in front. So arcsine U's derivative is just a negative version of that. So it'll be negative U prime over the square root of 1 minus U squared. The derivative of arc cotangent, which is the negative U prime over 1 plus U squared. And then for arcsecant, negative U prime, F's value of U, square root of U squared minus 1. All right, so let's practice applying these rules here. So we're going to find the derivative of arc sine of 3x or inverse sine of 3x. So you see that these notations are going to get flip-flopped, or they're going to be used interchangeably. So we just have to kind of get used to the fact that, okay, sometimes you may see it as inverse sine, sometimes you may see it as arc sine, but they both mean the same thing. So we're going to apply the rule here, which is U prime over square root of 1 minus U squared. So U prime, again, whatever's inside the parentheses is your U value. So what's our U prime going to be? Just 3. Okay, so 3 over square root of 1 minus, 3x quantity squared, which I can reduce to just be what? 9x squared, So whatever this graph looks like, this is going to describe the slope behavior, slope pattern of this graph, the original graph. All right, number 2, we'll use the U prime over 1 plus U squared. So what's U prime going to be? 4x over 1 plus, and then 2x squared quantity squared, which will just be 1 plus 4x to the fourth. Okay, try the last one, try number 3. We can actually reduce here. You can reduce inside an absolute value, so the 5 and 5 can cancel out. Now, 4 and 5, we're just reducing, simplifying the following expressions. So again, just show that you can cancel across what's inside an absolute value. So this one would just be 3 over absolute value of x. So it'll be 2 over absolute value of x. The graphs of these inverse trig functions, not a huge deal in terms of we're not going to be you're not going to be asked to graph, but I think it's just good to know. So inverse sine function kind of looks like a sine function that's kind of flipped sideways. So it goes something like this. And the reason why there's restrictions is because if it keeps going, if we keep following that pattern, it's no longer a function, no longer pass vertical line test. So we have these restrictions for domains so that our inverse sine function can still remain a function. Otherwise, it'll just look like an S, and it'll just keep going down or keep failing the vertical line test. So it's forced into a restricted domain so that it can be still called a function. So the domain is from -1 to 1, and then the range extends from -π/2 to π/2. Inverse cosine function looks something like this. From pi to 0, from 0 to pi is the range, and then from -1 to 1 is the domain. And then inverse tangent, instead of vertical asymptotes, now we have horizontal asymptotes at -π/2 and π/2. All right, let's evaluate some inverse functions here. Let's try. Now we try 6 through 8 here. We have arc sine of x. Evaluate the function at x equals √3/2. So this is just using unit circle knowledge here. So f of √3/2 is equal to arc sine √3/2. So again, arc sine, arc trig. Another way to think about this is it's basically the same, asking the same thing as, what theta value will allow sine of theta to be √3/2. And for sine, you're always looking for your solution between the fourth and the first quadrant. And because we have positive, anything positive is always first quadrant. So sine is going to be √3/2 when theta is equal to pi/3, right? If I plug in -2 in for x, I'm looking for inverse cosine of -1/2. But that's the same thing as saying cosine of what theta value is equal to -1/2. And the output for inverse cosine is going to be either first or second quadrant, and second quadrant if it's negative. So it's going to be that pi/3 family, the second quadrant, so be therefore 2 pi/3. This is the same thing as saying arc tangent of 1/√3, which is the same thing as √3/3. So anything positive, is in the first quadrant, and 1/√3 is going to be in that pi/6 family. Okay, so let's do some practice problems here. So try the odds here, 1, 3, 5, 7. So 1, 3, and 7 are new rules, but 5 is one of the original 6 trig rules, right? So look back at your rules and see if you can apply these derivative rules there. Okay, so number one, arc sine of u is u prime over square root of 1 minus quantity, u quantity squared. Arc tangent of u is u prime over 1 plus u quantity squared. And then cosecant of u, so I'm going to go and talk about how we're going to adapt all of our previous rules with a built-in chain rule. So in this case, cosecant of u is negative cosecant u cotangent u times u prime. So normally we learn cosecant of x as negative cosecant of x cotangent of x, but now we're just going to replace every x with u and then always attach it times u prime. So now we're going to revisit all of our derivative rules with the chain rule built into it. And then number 7, arc cotangent looks a lot like arc tangent. It's just the negative version of this. So negative u prime. And my u value is already negative, so 2 negatives makes positive. 1 plus u quantity squared. So just 1 over 1 plus x squared. Okay, so let's try 11 together. 11, it says find the tangent line of the curve at a given point. So what we're going to do is we're going to find the derivative, plug in the x value to get the slope, and then we can plug the x value into the original function to get the y value. And then once we have our ordered pair and our slope, we'll put it together as point slope form. So I'll work through number 11 with you, and then you guys can try number 12 as well. Okay, so my derivative is just u prime over square root of 1 minus u squared. I plugged in root 2 over 2, and for x, and do the derivative to get my slope. If I do root 2 over 2 squared, that's the same thing as 2 over 4, which is the same thing as 1/2. 1 minus 1/2 is 1/2. And if I divide by root 1 over 2, it's the same thing as multiplying by the reciprocal. So the reciprocal of root 1 over 2 is root 2 over 1. So that comes up to the numerator. So my slope is root 2. Now I have everything that I need to build my tangent line equation. All right, try number 12, same process. Find your order pair from your function, find your slope from your derivative, and then point slope form. Okay, any questions with 12? Okay, let's look at 19 below here. So here, they're asking us to find the derivative. What's needed here, just by looking at the way this is set up? Okay, we definitely have to involve arc trig rule. We definitely have to involve natural log rule. Something else. Something about the y here.
Implicit.
Implicit, yeah. If you see y out of place, if y is either stuck inside the equation or y is raised to a power other than 1, or there's multiple y variables, those are indications that we got to involve implicit. So, you know, your ui dx will pop out as you go through your derivative process. So our tangent of u is u prime. So the derivative of y is 1 dy dx all over 1 plus y squared. And then natural log of x's derivative is what? Yeah, 1 over x. I can cross multiply here, just so I can get these fractions out of the way. Now I can just divide by x to isolate my derivative variable. Hey, any questions? Okay, if you can turn to page 22, some practice problems here. But I want to use the space here to kind of just want to revisit these derivative rules in terms of maybe some strategies to help memorize these, especially these trig derivative rules. They all, they all look so so complicated and involved. So this is a way, at least the way that I look at it. If I can find a bunch of patterns, it helps me remember the rules easier. So let me have you guys write these out again. So you have derivative of arc sine of u. You have derivative of arc tangent of u. And you have derivative of arc secant of u. These are the only 3 main ones you need to know, or at least among the 6 arc trig rules, because you know that if you can memorize these 3, then you know the other 3 that involve C's, arc cosine, arc cotangent, arc cosecant, are just the negative versions of these. Okay. So looking back at these rules, what common thing do you see amongst all these 3 rules? Yeah, they all have they all have fractions. They all have u prime in the numerator. So we know that the numerator is going to be easy, right? So it's the denominator that's going to potentially give us trouble. What common things do you see in the denominator? They all are just mainly just 1 and u squared. I know arc secant looks more complicated with that absolute value, but they're mainly just 1 and u squared for the most part. And arc sine and arc secant, they look like, oh, we have to maybe memorize what order those terms are going to be in. Okay, so let me show you just the way that I do it here. So I know that they're all going to be involving fractions. So that's going to be easy. The numerator is easy. They're all going to be u prime. Next, I start with the easiest rule, which is arctangent. Arctangent has no absolute value, has no square root, has no minus sign. It's just easy 1 plus u squared. So I start off with that 1 plus u squared. You can also do u squared plus 1. The order doesn't matter. Next up, I go to the most complicated one, arc secant. I know arc secant has that absolute value of u sitting in front. I know it has the square root. And I know inside it's going to be some combination of 1 and u squared. And what helps me remember it is I know that u squared comes first because I know the u's are next to each other. So that helps me remember, oh, it's going to be u squared minus 1 and not 1 minus u squared. And if I can see this pattern in front of me, then I know that my arc sine is going to be slightly different. So instead of u squared minus 1, it's going to be what? 1 minus u squared. So that's how I go about forming my derivative rules. You may have different methods, but I just want to show you my way of organizing my my pattern amongst those three rules. And again, if you have these three figured out, then these three should be easy because you're just copying the rules and then just making them negative in front. Okay, so let's try through some of these here. So starting with 1, what is the slope of the normal line? So normal line means perpendicular line. So let's find y prime of -1 for this function. And then we can just take the opposite reciprocal to get to the perpendicular slope. Oops. Oops. Number 2 is a nested chain rule here. Just for reference here, the derivative for e to the u is e to the u times u prime. I know that so far we've only learned e to the x, but we know that if there's chain rule built into exponential function, e, we know is going to be the original function times the exponent's derivative, so e to the u times u prime. But then within this, there's a larger rule, which is arc sine. So arc sine of u is u prime over square root of 1 minus u squared. U prime is asking for the whole parentheses derivative, which is e to the 2x times 2. So e to the 2x times 2 would represent the full derivative of my parentheses, which I have to go through a little bit of chain rule to get to that derivative, all over square root of 1 minus e to the 2x quantity squared. And if I have exponents next to each other, I'm just going to multiply them together. Right, number 3, this is inverse function derivative. So I like to go through that chart that we've been practicing with. So I'm looking for G prime of -3. I know G and F are inverses of each other. So without even looking at the rest of the chart here, or look at what they're given to me, I know -3 is the x value of my inverse function, G function, which must mean that -3 is the y value of my F function. So they tell us that G of -3 equals 2. So therefore, I know there must be a f of 2 equals -3, right? We know inverse functions are going to have flip-flop order pairs. So then if I know what f prime of 2 is, then that's going to lead me to the slope of the G prime of -3. So f prime of 2 is -1/3. That's given to me. So therefore, G prime -3 is what? -3, right? I'm just going to flip the fraction, but I'm going to keep the sign. So just -3. Chain rule here. We know arctangent's rule is u prime over 1 plus u squared. So u prime, derivative of cosine is negative sine over 1 plus. Okay, page 23. Because I know I'm looking for f prime of 9, I can just go ahead and set all this up without even looking at the rest of the problem. And now I'm just trying to fill in the blanks here. It's nice that they're giving you the order pair. They're not going to go through guess and check or trial and error. Okay, we haven't fully gone into problem like number 6, but we're going to get to the second derivative. So think of position as your original function. Your velocity is your f prime, and then your acceleration is your f double prime. So when it says acceleration, we're just going to make our way down to the second derivative, and then we'll plug in 1 to get that acceleration value. You will use your arc trig rule to get to 1 plus 1 over 1 plus t squared. And if you want to find the derivative again, you could go through quotient rule, or you could bring that 1 plus t squared up and go through chain rule to get to the second derivative, which I'm going to do. I'm going to prefer chain rule, especially if I can avoid quotient rule. So outsize derivative, bring the -1 down, keep the parentheses, subtract 1 from the exponent, and multiply by the inside function's derivative. Now the second derivative is at the acceleration level. So plug 1 in for t, and whatever numeric value you get will be the acceleration at that moment in time. Okay, so your homework, we've done majority of page 16 and 17. We've done majority of page 22 and 23. So if you can finish up these two problems, and also page 16 and 17, which is more implicit differentiation in practice. So I'll send out a reminder this afternoon. Okay, so homework page 16, 17, 22, and 23. Your homework there. Yes. Yeah. 9 through 15.
So I got 16 wrong, but I have 14 through 15. No, I thought it was 9 through 11. It's 9 through 15. You need to go through.
Yeah, but you just said that.
Yeah. 9. And I didn't.
And 16.
Yes, and then.
Yeah. So go ahead and write that down. Write these down. Hey, James. 14, 15.
Well, I'm trying to say, I feel like. It's not Dr. Marsh that he makes you like say and this, so.
It's my mom, like, yeah.